Thank you all for coming. Good afternoon to everyone. And of course, I want to thank the organizers and the main organizer, Professor Selman, for inviting me to give this lecture. Before I start anything regarding this topic, I would like to emphasize that this lecture is dedicated to the memory of late Professor Bojan. Many of you, most of you knew him. You know that he left important trail in the scientific and personal sense, and we miss him very much. Regarding this study, he was a part, or for most topics, he was an initiator of research, which I will present today. That is what I wanted to mention before I start with the presentation. And the topic we are dealing with is our two specific geometries of specimens for pipeline material testing, and to be more specific to pipeline material fracture mechanics, determining the parameters, fracture mechanics parameters suited for pipeline material. Of course, like in any other field, the determination of fracture resistance and more wider field is important. Here it is in process industry. For all other geometries, of course, in all branches of industry, integrity is and the fracture resistance is, of course, the most relevant topic. The problem is the problem with the pipeline testing is that most of the pipelines are thin-walled, and I will discuss a little bit how to approach to the fracture testing because the standard specimens are specifically plane strain, in other words, thick specimens. Like I said, two geometries will be mentioned. I will introduce them later. Just a few seconds on the basics, which we of course all know. Main aim is to determine the elastic plastic fracture mechanics parameters, which are corrective opening displacement and J integral. But having in mind that generally the most often approach is to calculate the J integral based on the summation of elastic and plastic part. Of course, stress intensity factor is also important for it. So in this typically used equations in different forms, two of the members are most important, and those are the members we calculated for our geometry. This is stress intensity factor and eta factor, which is for plastic part of the geometry. As soon as we look at the standard specimens, we see this specific requirement for sufficient thickness, which is necessary to determine the critical values of the K, J, and CTOD. And if these conditions are satisfied, we can call them the plane strain fracture toughness, determined via any of these three parameters. Now, here we have the problem because the specimens are thick and the pipelines in the most industrial applications are thin-walled. So the question is how to let's say how to establish a relation between an actual situation. The best way to let's say establish the conditions which are like exploitation is to test the pipe itself. It is sometimes done, of course. These photographs and the drawings are from PhD thesis done under mentorship of Professor Sedmak and Professor Rakin, I think about 15 years ago. Dr. Živče Šarkočević was at that time a PhD candidate. And the topic was to determine the influence of a particular crack or a particular volumetric defect on the integrity of this geometry. So in the laboratory, the ends are welded to the pipe, the internal pressure is introduced, and so on and so on. So basically, between these two extreme conditions, the standard specimens and real actual conditions in the pipes, in the recent, let's say, 10 or 15 years, there have been many studies worldwide where several groups of authors proposed the geometries specifically for testing the fracture behavior of pipeline materials. The first of these geometries is general and well-known sand specimen, single-edge not-tandem specimen. It is introduced a long time ago, and the example of these images are from a paper of Professor Julien Zhang and his co-workers. I am giving these figures not because they were the first ones to establish this geometry, but because this paper is a very elegant way, in a very elegant way, it proves that for axially loaded pipes, the sand specimen represents better the fracture conditions and stress state in the pipe. I emphasize with circumferential. So sand specimen, it can be said that it's widely accepted for such geometry of the crack. Another attempt is shown on the right side of this slide, where the authors tried to emulate the shape of the compact tension specimens by welding these additional levers to the pipe segment. So basically, they made a combination between the standard geometry tools and everything, and actual stress state in front of the crack tip. This can be said that it's maybe a universal way. All subsequent geometries I will mention try to do this, to establish a testing procedure which looks at as much as it can as the standard specimen testing, but keeps the conditions in front of the crack tip in an actual piping. Axial defects, cracks, and sharp notches are the main focus of our studies. And one of the geometries presented in the literature is given here. It is actually compact tension shape, but cut from the cylindrical geometry. And because this geometry is non-planar geometry, specific tools are needed to establish deformation in hook direction. This is one of the proposed geometries in the literature. In this work, authors proposed several, in my opinion, very interesting geometries, because they tried to emulate practically all the standard fracture mechanics specimens, from compact tension, single edge notch bending. There are even more. They developed 8 geometries for this figure, and the downside of this approach is that this type of application requires a lot of plastic deformation to the material, which can, of course, affect the stress state in the material, just like welding or other preparation procedures. I will only mention another very recently published specimen geometry. This is a ring specimen exposed to tension, so basically very similar to our specimens. However, I would like to emphasize the position of the crack. It is an axial crack, but a crack which goes along the thickness of the pipe. Therefore, if we think about the application to metallic pipelines, it would be best suited for thick pipelines, and this cross-section geometry is very similar to the classic thick-walled sand geometry. However, the authors of this study, as far as I know, have applied it so far to polymer materials, not until now to steel or other metallic pipelines. This slide contains 2 geometries which have been developing for, I don't know, one of them at least 10 years, and the other one is relatively recently introduced. Just like all other geometries from the literature, we had an idea to have a geometry that resembles some of the standard ones, but to adjust these to the pipeline testing. So we have ring specimens exposed to either bending or tension loading. Bending specimens have been patented by Professor Nana Bojan and Professor Yuri Matvinko, I think in 2015. And since then, a lot of work has been done in these specimens. All of us published probably more than 10 papers in those journals, mainly from three groups: group of Professor Bojan, group of Professor Dragan Kozak from Slavonski Brod. They are both here at the conference. And our group, like I said, led by Professor Rakin and Professor Sedmak, was also included in the work on this specimen geometry. Regarding the tangent specimen, which is shown in the lower part of this figure, the difference is only in loading conditions. So basically, we don't have a 3-point bending, but we have special tools which introduce the loading, which resembles internal pressure. So basically, the main motivation why trying to introduce this specimen geometry was to, I must emphasize, try to resemble the internal pressure. And on the right-hand side, there are examples of numerical models and meshing, because I will show a few numerical results as well. One of the main aims which we had when we started on this was simplicity. To have simple geometry without welding, without plastic deformation, or any other operation that could compromise the stress state in front of the curve. So basically, cutting the ring and preparing the defect, that's all that is required. I'm giving here only a brief extract from our published results. This one is a comparison between specimen exposed to bending and the classical sand specimen. We had the comparisons of the force displacement curves, the crack growth curves, and so on and so on. But this little comparison gives us triaxiality. We have proven that despite the irregular shape of the irregular distribution of the J integral in front of the crack tip, triaxiality is very similar, which is crucial for ductile structure development. And practically most of the pipeline materials behave in this manner. So, in development of these bending specimens, Professor Bojan and his group created a large set of specimens cut from a single plate in order to be able to compare experimentally and later numerically behavior of these shapes cut from the same pipe to the same material and so on. The next step was obviously to cut the specimens, ring-shaped specimens, not from the plate but from an actual pipe. And this is a very simple scheme which is shown. And this was the topic of a PhD thesis done in our faculty, where thin-walled pipes are examined. Practically same geometry, differences in the thickness of the model. And here I will present one specific result. We had the chance to have one of the pipes had thicker walls. So we were able to fabricate a very thick specimen, compact tangent specimen, and use it for verification of parameter transferability by using the complete Gerson micromechanical model. This slide is only mentioning of different micromechanical local approach models. What we used was the complete Gerson model developed through a separate team by previously mentioned Professor Bojan from NTN. When we applied the micromechanical approach to this available compact tangent specimen and appropriate ring, we verified that these parameters determining the correct growth can be transferred, and therefore we obtained for all the thin-walled pipes, we obtained let's say fictional compact tangent specimen results. In other words, based on the thin-walled specimens, using the micromechanical analysis, we obtained the plane strain conditions and determined the conditions that couldn't experimentally be obtained. So we established a relation between thick-walled standard specimens and thin-walled specimens one of the also and another example of the results obtained on a thin-walled pipes, ring specimens, is shown here. Those are crack growth curves, where crack growth is determined by normalization procedure, and fracture mechanics parameter is crack tip opening displacement determined by delta 5 concept from GKSS. Two things I will emphasize here. First, diagram shows us very repeatable results. Those are the specimens with one of the stress concentrators in the seam, in the longitudinal well. And we can see here very repeatable results, irrespective of the geometry of the specimen. And on the other, we can see that the influence of the material properties has been captured successfully, because the well seam of this seam pipe had much lower resistance to crack growth, to ductile crack growth. This can partially be seen through sizes of final cracks shown in the photograph in the lower right. In development of the tangent specimens, we had a different approach. Namely, we didn't cut the steel specimens in order to compare them with standard ones, but we have fabricated polymer specimens by 3D printing. It was done in the framework of the PhD thesis of Dr. Isak Lajkovic. I must also take time to brief our dear Professor Jojan and thank him for coming. So, like I said, for this geometry, initial materials were not steels, but 3D printed polymers, because it enables us to, let's say, rapidly fabricate a lot of specimens, and also to apply this approach to other materials, not only to steels. For this geometry, it is rather important to mention that it can be with one stress concentrators. This is something that couldn't be done on bending specimens, and this led to a problem that we don't know which one of the stress concentrators will be the first fracture initiation site. On this tangent geometry, on a 3D polymer specimens, we have the first result I'm showing is, let's say, an additional one. This was not the primary goal when we started working on the polymer specimens, but this is a sequence of digital image correlation, from digital image correlation software, where we track the strain field in front of the crack. Therefore, we managed for these materials to determine the dynamics of the crack growth, and this is something which cannot be done for steels, having in mind the shape of the crack, which is much more pronounced in the middle than in the surface. So basically, this was something that we were able to do just on the 3D printed polymer specimens. Now I will show something that I mentioned in the very beginning. In order to calculate the J integral from examination of these specimens, it is necessary to calculate stress intensity factor and eta factor. And I'm back now to the probably first slide, and extracted values of stress intensity factor from numerical models of these geometries have shown us two things. First, that the results with 1 and 2 stress concentrators are similar, and the second, that the distribution of the J integral and therefore stress intensity factor is rather irregular, and maximal value is obtained near the surface of the specimen. So this is a very important difference between standard and ring specimen. Fortunately, when we examine later the shapes of the of the cracks obtained by ductile fracture on steel specimens, such a distribution of the fracture mechanics parameter did not influence the cracks, and they all grew so that maximum value of crack growth is obtained in the middle of the specimen thickness. After this, we made a series of geometries and determined the dependence of K on geometry of the crack and of the geometry of the specimen and geometry of the defect. And we have obtained a certain dependence, which needs to be, of course, adjusted for the particular 5 dimensions. So this should be, and we will do it, prepared for a wider range of 5 geometries. After that, eta factor for determination of plastic component of the J integral is calculated. We use 2 methods. One of them is load separation, and one of them is so-called direct method, where we calculated the J integral based on the domain integral method from Abacus, and then based on the all obtained curves, force displacement, surface under the low displacement curves, and so on. We use backward analysis to determine eta factor for all examined geometries. And when I say all examined geometries, we took as a basis the dimensions of the rings which we experimentally examined, and then varied the correct length, and varied thickness, and some other parameters, also diameter. So for our examined material, we have created a series of numerical models. All of them have some differences in comparison with the actually examined. For all of these geometries, expressions for eta, so we can analytically calculate eta, are given. Let's say one of the examples is here. The equation given in the lower right is for one of the 5 geometries, and we have here dependence of eta factor on the size of the stress concentrators, on the ratio of the size and of the specimen. When we, let's say, compare these specimens, we can say that, of course, they are not on the same level of development. We have much more work done on bending specimens, and tangent specimens are, let's say, current work, and we will continue working with them. One of the good things is of the bending specimens is that they can be tested completely using the standard tools. Tangent specimens require 2 specific tools for specific 5 diameters, but we can test the geometries with 1 stress concentrator, which is very beneficial. And both of these geometries can be said that they are advantageous because they are simple, and this simplicity enables us to have the stress and strain state exactly like in the pipelines in exploitation. Like I said, despite the fact that the ring specimens have irregular fracture mechanics parameter distribution, tactile crack growth was really regular from initial sharp notches. I will end this with a problem that we encountered that is typical for such geometries, which is a formation of a pre-crack which could have a regular shape. It turned out to be very problematic. We had some attempts to solve it, but for now, the main way is to test the very sharp notches obtained by laser cutting or by electric discharge machine. I have some conclusions here. I mentioned all of them, so I wouldn't take too much of your time. I'm sorry if I too long into detail.
It's okay. Thank you very much, but we will leave discussion for the end.